Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. And I am very happy to have back, first person to have 2 videos, Deborah Domingue. Hi, Deborah. How are you?
Pretty good. Thanks for having me again.
Oh, it's really lovely. You have a very awesome looking astronomy mission kind of artwork over your left shoulder. If I got the parody right there. What is that?
So that's a batik that I found in Japan, my first trip to Japan.
Cool.
And I found it in a kimono shop. And it's a depiction of the first Hayabusa mission.
Okay.
That went and sampled the S-type asteroid Itokawa. And when I saw that, they didn't have any for Hayabusa 2 yet, but I had to have it.
That is very awesome. Very awesome.
Yeah.
It's a nice piece of artwork too. I like the spacing of the design elements. It's lovely. It's very cool.
Yeah. So the general public were very, very proud of this mission. And so you could find souvenirs of this mission. I found these before Hayabusa 2 had arrived at Ryugu. But yeah, it was fun.
Do you have a little? Do you have a little?
I do. My little spacecraft.
Put it up to the camera. That is so.
I bought that at the gift shop at ISIS JAXA. That's there, similar to NASA. I bought this.
So it's like a gift store in the bottom or something.
Say again?
It's like a gift shop.
Yeah, it's like a little gift shop. You know, you can buy your souvenir T-shirts and
cool.
you know, your spacecraft.
I love it. I love it.
I do too. It's on my desk.
Gonna have to get one. Very cool. And speaking of those 2 missions, this is going to bring us to this really lovely science article. This is a Planetary Science Journal, open access and spectrophotometric properties of 162173 Ryugu surface from the NIRS-3 opposition observations. And Deborah, take us away.
Okay, awesome. So first of all, I'd like to give a shout out to all my co-authors who really contributed to this work and helped make it happen, to the operations and engineers at Hayabusa 2 who really flew an excellent mission. We made the great science happen, so I really want to say thank you. This particular paper focuses, as the title says, is on opposition observations. And for those who are not familiar, you know, light comes in at an incidence angle, reflects off at an emission angle, and the angle between the 2 is phase. Well, opposition is when that's close or 0, very, very small. So in the case of these observations, you had Ryugu, you had Ryugu, the spacecraft.
There you go.
And if my face is the sun, that's how it was, you know, one right after the other. So the sun was behind the spacecraft and the asteroid was in front of the spacecraft. So that's kind of.
It's a full Ryugu.
Yeah, a full Ryugu, yes. So if you scroll down, I think it's the first figure.
Sure. And there's Hayabusa 2.
So this study focuses predominantly on the opposition data. And what you see here is the footprints for the spectrometer. NIRS-3 is the spectrometer that was flown on the Hayabusa 2 mission on that spacecraft. You see it plotted up against or mapped on the a mosaic of the surface from the optical navigation camera, the ONC. That was their imaging system. It served both for science and for navigation. So the observations we're looking at are the ones in color. Those are where the footprints fall. And they were of different resolutions because some of the times we were far from the asteroid, other times we were up close. So the footprint changed. And one of the things this paper did was to take a look at, did the footprint size matter? And
cool.
And it also took a cursory look. Let's see, I think if you go to figure, the best one will be figure 8. Looking at them here.
Take a look at figure 8.
We also took a look at.
Good detail. Okay.
There we go. Okay, so these data were not taken in opposition. I'll show you a comparison of the opposition data. But we looked at basically from 0 to about 16, 17 degrees in the data set that we analyzed for this study. And what you're looking here is our spectra taken across the surface, different footprint sizes, but all at very much the same, illumination and viewing geometry. So incidence, emission, and phase are very, very similar.
Okay.
And what you see in the upper left is the solid lines are the observations themselves. And this is the variability you have across the surface.
Ah, okay.
Okay.
Got it.
Same footprint size, pretty much same footprint size. This is the variability you have. But if you take those spectra, and you normalize them, let's say, okay, all the spectra are 1 at 2.2 microns.
Okay.
How do they compare? And that's what you see on the upper right. And if you notice, all the solid lines are smack right on top of each other.
Indeed.
So the big difference across the surface is not so much in the spectral properties, the little wiggles and the slope of the lines and all that, but is in the overall brightness. So there's this darkening agent on the surface that is more in some places and not as much in others.
Yep. Yeah.
All right. And it's pretty spectrally neutral because, like I said, you're not seeing any slope changes. You're not seeing any absorption feature changes.
Right.
Now,
let me ask a question. So, the spacecraft was in orbit around.
Well, ironically, it was not in orbit. It hovered.
Okay, that's where I was going with the question. So, when you do a scan across the surface, that was basically a single take, or were you able to do multiple scans across the surface?
So here's your handy dandy spacecraft, right?
Yep.
And here's Ryugu, my fist. I don't know. Let's see if I can do this. All right. So the spacecraft is actually hovering over the surface, and it's taking observations as the asteroid rotates.
Oh, okay. Somebody's rotating. Okay.
Okay. So the asteroid is rotating, and it is just taking so it's taking observations of the surface that Ryugu is presenting at that time.
Gotcha.
Okay?
Gotcha.
And it has a rapid enough orbital period, and I don't remember it off the top of my head. It's on the order of hours. So you can still get that same illumination and viewing geometry for quite a bit of the surface as it rotates.
Yeah. Okay.
So that's why when you looked at figure 1, the observations were like lines in longitude. They were across in longitude. And the bottom row of these in this figure are, once again, just slightly different phase angle. But you notice that in this case, the darkening agent or whatever is changing the albedo of the surface, for those areas, it's all very, very similar. And when you normalize it, you look on the right, there are no, the slopes of the lines are similar, they're right on top of each other.
Similar in shape.
Right?
Some a little more, some a little less, but yeah.
Yeah, there's, within the measurement areas, these are identical. The dotted lines in all these graphs so what we did was we applied a model to these observations with a photometric model. Basically, it predicts what the brightness should be as a function of wavelength and as a function of incidence, emission, and phase. And
pretty good.
This model is applied to the data set as a whole.
Okay.
It's not applied region to region.
Yeah.
So
global. It's a
global fit. And so it's a global prediction of what, on average, Ryugu's spectrum will look like this. And so the dotted lines are simply predictions of the solid lines. And
pretty good prediction.
Well, in some cases, a very excellent prediction, right?
Yes.
You see across the bottom, it's smack on.
It's
right. For the top ones, it doesn't capture the variability, but that's the nature of the model. The model is modeling a global property, not so it's one way of showing, hey, this is how on average what Ryugu should look like, and this is the type of variability we're seeing. So there's some mineral, some opaque, we haven't quite figured out, and in the case, this is a very, very dark object. It's carbon rich. Put two and two together, it's probably carbon. The absorption feature you see around 2700 nanometers, that's a hydration feature. So we know we have a clay there. And that was discussed in Kitazato et al. Their initial their science paper. The initial results from the mission.
Very good.
But so one of the things about the photometric modeling, and that's what the paper focuses on. We had this beautiful data set. We applied a photometric model, and yes, it can predict the spectra, or tell us the variability from what a global surface, an average surface would be. But the nice thing about photometry is it also tells us about the structure of the regolith.
Okay.
Just think for a minute. If you are standing on a sandy beach,
okay,
how light is going to reflect off that sandy beach versus if you're up in Maine on the New England rocky coast, it's going to be very different.
It will.
Okay. So one of the drivers for doing photometric modeling is to try and understand a little bit about the physical structure. And in this study, I'm going to focus on three properties.
Okay.
One is what we call granularity.
Okay.
That's, do I have a slab or do I have a powder? Excuse me, that's the dog.
Hello, doggy.
Yeah. So do I have a slab or a powder? Okay,
no,
so
you're good.
We're going to look at granularity.
Yeah, you're doing great.
One is grain size.
Okay, so granularity, grain size.
Grain size. And the other one is porosity. It might really compact, or like the moon with its fairy-castle structure and its regolith. It's got a very, very fine gray regolith, and it's very porous. So it's the structure is very what has been dubbed a fairy castle. Spires and tendrils and all that fun stuff. It's not like I've sat down and I've compacted, my brown sugar, and I've compacted it into my cup.
Okay.
Okay. So if we go to, I think it would be figure 13.
Figure 13.
I know I'm bouncing around.
A little farther down, 12 and 12, one more, 13. Here we go. I'm going to zoom it out just a bit to get the whole thing on there. There we go. Okay.
What I want. Okay, so when we looked at our spectra that all lined up on one another, there are a couple of things you can examine, and one of them is spectral slope. You can fit a line between like 1.9 and about 2.6 microns, and you can fit a line to how it's pretty linear. It's got its little wiggles, but it has a spectral slope. And then you can look at how that slope changes based on the phase angle.
Yep. And
that's what we're plotting here. That's what we're looking at here.
Okay.
And the different colors, it's segregated based on incidence angle. So one of the things we can do, or one of the things that has been done, is we can go in the laboratory and you can take different meteorite powders and you can measure the spectral slope. You can measure it as a function of phase angle, and you can control the properties of your sample.
Yes.
I can have something that's porous. I can have something that's compact. I can have something that's got really, really small grains. I can have something that has really, really big grains, right? And you can notice some trends. All right. Or I can take my meteorite and just have a slab.
Big.
and measure the same things off the slab.
Mhm.
And
Cool.
so one of the things we could do, so when I talk about granularity, I can answer the basic question, am I looking at a slab or a powder?
Yes.
What is my surface like? Is it all these rocks, these big, huge rock chunks of rock that will behave like a slab? Or do I have some fine grained powder? Do I have powder in there anywhere? All right. And when you look at the trends you see in the laboratory, and then you compare with the trends you see here,
Mhm.
we have powder.
Okay.
Okay. So that's one of the things we look at here. We have powder. We have there's this wide range of grain sizes, but we've got some of the small stuff in here.
Okay.
Okay, and that's a big thing to take away. It's not a bunch of slabs, not just a bunch of big rocks.
Right.
We have powder, and some of that powder is fine grain.
Okay. Mhm.
Okay, and the other thing too is that packing, when you can pack something, it tends to give it more of a bluer slope. That means as wavelength increases, your reflection decreases.
Okay. Yeah.
We see the opposite. As for Ryugu, as the wavelength increases, the reflection also increases.
Okay.
So there's some amount of porosity in,
Mhm.
right? It's not a finely a compact surface would be blue.
Right. Not brown sugar.
So if we go to figure 17,
17. Okay.
that would be kind of fun.
Back.
And
15.
in here, I mean, as you're scrolling by all of that, you know, we did comparisons with ground base, we did comparisons with the camera system. But one of the other things we did was we compared with similar studies with other objects.
Oh, nice. Nice. Okay.
Okay. So you see that the orange is Itokawa. We have the moon. You always compare with the moon because why?
What- yes. There's the moon.
We compare now. Note that the NIRS 3 data is the wavelength is all near infrared. Most of these studies, these similar studies, have been done in the visible wavelength ranges.
Yeah.
So we included here, if you look at that red circle.
Yep. ONC-T.
Yeah, ONCT. So that's the Hayabusa 2 visible data was from the camera. They had several bands in the visible wavelength.
Okay.
And so if you plot the results by my colleague, Eri Tatsumi, in the visible, that's where Ryugu falls. But this big cluster above it of the blue diamonds,
Yes.
this is where Ryugu falls in this diagram in the infrared.
Right.
Okay, in the infrared. And for anybody who does modeling with the HACD model, they'll recognize the axes on this. You have the amplitude of your opposition, that's B0, and then you have how wide your opposition is, that's the H.
Okay.
And so we're able to compare with different asteroids that have been visited by spacecraft, by the moon, our own visible observations, and
Comet.
so we're seeing basically a surface, at least based on the visible, that's not too different than other asteroid surfaces. It's
Okay.
a little different from the moon.
Yes.
Okay,
Yeah.
we don't have a fairy castle structure here. I mean, that's pretty obvious when you go look at the images, by the way. Let's go look at the images. They're at the bottom of the paper. I forget. I think they're figure 19.
Okay. Oops. 18.
And I'm oh, let's stop here for a second.
You want to stop at 18? Okay.
Yeah, we're gonna stop at 18 first.
18's good. Details
So-
are great.
One of the things that, if you look in the literature, looking at how
Okay.
they look at a ratio of the surface brightness at 3 degrees phase
Yep.
versus 5 degrees phase.
Okay. Mm-hmm.
And they've done it, and they've looked at this property predominantly in the visible. So one of the caveats here is we're looking at the infrared, but these measurements have been made, and you can see for a bunch of different classes of asteroids. And I do plot the in red is what we have in the visible from Tatsumi et al. In their paper.
That's right.
But notice in the infrared, we're down at the bottom. Near the
Yes.
Or yes.
These two.
So Ryugu behaves differently in the infrared than it does in the visible. In the visible, you can see that Ryugu is a C-class asteroid. No surprise, we knew that going in, but it's nice to have it confirmed.
Good. Good.
You know, it's nice to see that this is consistent. Now we can go to figure 19.
I'm sorry, say it again.
Now we can go to figure 19. I'm sorry.
19. That's okay. I'm good. Okay, let me pull out just a bit. There we go. Boulder.
So this is
Size.
the surface of Ryugu.
Ooh,
This is what the camera sees.
very cool.
And you can imagine when they had this lovely spacecraft. Let's bring it up here. So this black arm here, that's the sampler. They actually touch the surface, set off a pyro, and the material comes up and gets captured. That was the general mechanism. Okay, they expected an asteroid like Itokawa that had these ponds of fine grained material. There were no such ponds on Ryugu.
Okay.
So it was an adventure in engineering in finding a place that we could go sample without harming the spacecraft, you know, because this is what we had. This is what we had. And what's really unique about our study is that we verify that the surface isn't just a bunch of pebbles and boulders, things that would behave like slabs. There's definitely a powder component.
Yeah.
And in that powder, there's a fine grained component. And we saw a bit of evidence if you look at the videos of the when they took the samples, the material that came up and shot up. There's definitely some fine grained stuff in it. But that was the big, you know, and the big debate whether is there powder, is there not, is there fine grained stuff, is there not. This study falls on there's powder and there's some really fine stuff in there too.
Nice.
Whether it's coating,
right, or
coating, we don't know.
Right.
Or if it's, you know, really intermixed with the smaller rocks and all that. Right. We're looking forward to the measurements from the samples that were returned last December.
Nice.
To see, you know, okay, now that we have the remote sensing and we have the samples, are they telling a consistent story? Using both of them, you can even get a better understanding of what this option is.
Very nice.
That's the paper in a nutshell.
Very nice. Very nice. And we, of course, on this 22 pages, just touched on a couple of highlights. And so I encourage people to go ahead and read some of the other slightly lesser highlights, interesting nonetheless. So go ahead and check out this really lovely PSJ article. So Deborah, thank you so much for walking us through your article.
Thank you so much for having me.
And you touched on it a little bit toward the end there. And so I want you to kind of give it a future look, right, on where we go, you know, where does the community go over, let's say, 5 years. And you touched a little bit about some of the sample return missions. And, you know, I don't want you to spill any secrets you shouldn't spill or anything. Don't do that. But I wonder if there are you know, is there just one set of measurements and then, you know, it's all done, or is there going to be, you know, years of experiments on these samples that were returned? Is there plans for a Hayabusa 3, just et cetera? Just kind of, where do we go going forward?
So as I stated in here, this study was looking at the global properties. So now the next step is to look at the regional and the photometric properties of the regional areas. you know,
Okay.
like Eastern versus Western Hemisphere, poles versus equator, to see or better understand what variability there is and what is the nature of that variability. Because then one of the regions you look at are the two sample sites. So now you have remote sensing information about the sample site, and you have a sample. You have ground truth. You brought back ground truth.
Remind me, was that sample taken near the equator? Was it taken near one of the poles, somewhere in between?
So it was taking, there was two of them, and now you're stretching my memory, what sort of mid to equatorial latitude.
Uh-huh.
Okay, it was where there were fewer boulders.
Safer, yes.
You know, safe.
Safety
But
first.
we have two sites that we sample, and we have detailed remote sensing observations of those sites.
Mhm.
So now the job is to connect the remote sensing with the samples for the sample sites, and then extrapolate from there to across the whole surface.
Cool.
So that work is work in progress by many people. As far as Hayabusa 3, no word on that, but the Hayabusa 2 mission itself has an extended mission.
Oh, nice. Good.
And I don't remember the details. I will be long retired by the time it gets to its next object.
Okay.
But I will definitely be cheering it on.
Awesome. Very good. Very good. Deborah, thank you so much again for walking us through this really lovely article. And that will do, everyone. Thank you so much. And I hope this made your astronomy day just a little bit better. And we'll see you on the next one. Thank you.
Thank you. Bye-bye.